Assalamualaikum and hi everyone. We are from Group 4 for course TMF 121 for Computer Architecture course. Today, we will be presenting our group project which focuses on CPU simulation and cache memory performance analysis. Let me first start by introducing my team members. The first one is Alisha binti Abdullah. Second one is Nur Aisyah Umayyah binti Ahmad Jeffrey. The third one is Dayanur Nadia binti Muhsin. The fourth one is Wong Kun Yen. The fifth one is Shaw Li Xuan. And the last member is Chin Jok Cheng. For your information, each of us contribute different sections of the project, including research, simulation coding, and result analysis. So for the overview, we have two different tasks. The task one is RIC architecture and the second one is cache memory.
Hello everyone, I will explain our simplified 8-bit CPU design. It is perfect for teaching computer architecture basics. We will cover its key components and instruction sets. Let's start with the hardware. For the part 1, CPU components, our CPU has 5 main parts. First, the program counters. This is 8-bit digital points to the next instructions. Each can access 64 memory locations. And the next is the instruction registers. It is holds the current 8-bit instruction being executed. And then we have 4 8-bit general registers for temporary data store. And the next, the ALU purpose basic map and logic. It takes 2 8-bit inputs and processes and 8-bit results past data phase. Finally, our 64-byte memory store both programs and data. And next, the part 2, instruction design. All instructions are 8-bit long, split into 4-bit for the output, 4-bit for the overlays. We support 6 key instructions. First, load is move data from memory to registers, and the next is store. Store is set register data to memory, and the add and sub is perform arithmetic, and the TMP is change program form, and the last is hash. This is stop for execution. For example, 001 0010 means log into R0 for memory address 0 tied to 10. In summary, our 8-bit CPU demonstrated fundamental architecture principle is an easy to understand way. That's all for me. Thank you.
Hi everyone. Today we will demonstrate our simple RISC CPU simulator for question 1 of the TMF 1214 Computer Architecture project. So I am Chin Jok Cheng and my student number is 103658 and my partner.
My name is Chola Xuan and my metric number is 103698.
Okay, this simulator was developed using C++ and simulates a basic CPU architecture using the FAT decode execute cycle. Okay, our CPU consists of the following components: a program counter PC to track the current instruction, 4 general purpose register R0 to R3, 255-byte 56-byte memory array simulating the system memory, and an instruction set with 5 basic operation, which is load, store, add, sub, and hold.
Okay, so now we will run a simple program that demonstrates these instructions step by step. First, we initialize memory 100 equal to 5 and memory 104 equal to 7. The instruction sequence is as follows. First, we load memory 100 into R1. And then we load memory 104 into R2. Third is we add R1 and R2 and store the result in R3. And then the result that's stored in R3 is stored into the memory 108. And then lastly, we halt this program. Let's run the simulation together. Okay, so as you can see, after each instruction, the CPU prints the updated register value and selected memory cell. For example, after the add instruction, R3 holds the sum of R1 and R2, which is 12. And then we store this result into memory 108. The program halts cleanly after the instructions are executed.
Okay. This simulation shows how a RISC CPU performs each step in the instruction cycle. It demonstrates memory access, ALU operation, and register update. So, thank you for watching our demonstration.
Thank you.
Task 2 Cache Simulation. Cache memory is a small and fast memory that stores temporary data and instructions from RAM. When the CPU needs data, it will check the cache first. If the data is found in the cache, it is called a cache hit. But if the data is not found, it is called a cache miss. In order to make cache memory works well, it uses different types of cache, mapping techniques, and replacement policies. For our simulation, we use direct map. That means each block memory goes to only one fixed cache line. It is simple, fast, and no replacement policies needed. Next, why cache memory is important? It is important as it improves data access as it stores frequently used data close to CPU. Besides, it can reduce latency as it reduces the waiting time by giving data quickly to the CPU. In overall, cache improves system performance as the CPU gains faster data access and reduces delay, makes the system faster and smoother. Now I'm gonna explain about the simulation setup. These slides explain how we design and configure our cache simulation experiment. First, we tested two parameters, which is cache size and block size. As shown in Table 1, we varied the cache size using values of 4 KB, 16 KB, and 64 KB. Then, in Table 2, we varied the block size using the value of 32 bytes, 64 bytes, 128 bytes, and 256 bytes. These combinations allows us to observe how changing either the cache capacity or block size affect cache performance, including hit rate and transmission time. Next, under the replacement policy, we applied the command strategies such as LRU, which is least recently used, FIFO, first in, first out, and random. These policies determine which data to remove from the cache when it's full. LRU remove the least recently accessed data, while FIFO remove the oldest inserted data, and random selects a block randomly for replacement. Each policy was selected to test how it influences efficiency and data reuse. Now, finally, we used the DevC++ to develop and run the simulation. We implemented a directed map cache technique, which is simple and maps each memory block to one specific cache line. For the test program, we use metric multiplication, a common benchmarking test that generates a high numbers of memory access. To improve the accuracy, we also use a cache blocking, a method that breaks matrix into a small sub-blocks to match cache size. This improves the performance by reducing the cache misses and improving CPU access speed. In summary, this setup allows us to test how different cache configurations affect the memory performance and provide insight into which settings are most efficient.
Moving on to results and analysis. The figure shows the graph of cache performance with varying cache sizes. We can clearly see that as the cache size increases, the hit rate also increases, and at the same time, the miss rate decreases. 4 kilobytes has the lowest hit rate and the highest miss rate compared to 16, 32, and 64 kilobytes. It is due to direct map that only allows each memory block to go to only one specific cache line. So, when the cache is small, many blocks compete for the same spot, causing more conflicts and misses. But when the cache is larger, there is more space, fewer conflicts, and more data fits inside. This leads to a higher hit rate. To conclude, 64 kilobytes gives the best results as it has the highest hit rate and the lowest miss rate. It is more efficient and makes the cache system work much better.
The graph shows how different the block sizes affect the performance of a 32 kilobits direct map cache as the block size gradually increases from 32 bytes to 256 bytes. The cache hit rate decreases significantly from a 91.43% in 32 bytes to 33.33% in 256 bytes block size. This trend occurs because smaller block sizes allow more cache blocks, leading to a better data distribution and fewer conflict misses, which is ideal for a workload with a random or small memory accesses. In contrast, a larger block sizes reduce the number of cache lines, thereby increasing the likelihood of an overwriting useful data and resulting in a more cache misses. Therefore, the result indicates that a block size of 32 bytes is the optimal block size for maximizing the cache efficiency with a 32 kilobits cache. Based on the simulation of RISC CPU architecture and cache memory analysis, we can conclude that a simplified RISC design effectively demonstrates a key concept of a processor, operations such as instruction fetching, decoding, and execution using a minimal instruction set. The implementation of core components such as the program counter, instruction register, ALU, and general purpose register allow the execution of a basic arithmetic and memory operations, reinforcing how a reduced instruction set can maintain efficiency while simplifying hardware complexity. Meanwhile, the cache simulation revealed that the cache size and block size have a significant impact on the performance. Increasing the cache size from 4 kilobits to 64 kilobits improved the hit rate substantially, with the 64 kilobytes cache achieving a 99.6% hit rate due to a reduced conflict. Conversely, increasing the block size from 32 bytes to 256 bytes resulted in a lower hit rate with a smallest block size of 32 bytes, providing the highest efficiency by reducing the cache pollution and conflict misses. This finding highlights the importance of balancing the cache size and block size in designing an efficient memory systems. Thank you.
Challenges faced and how it's solved. The first one is understanding the cache concept. The challenge are concepts like direct mapping, cache blocking, memory layout were initially confusing. So the solution, we watched the tutorial video as an example power certificate and review the lecture notes and had a group discussion to improve our understanding. The second one is implementing matrix multiplication with cache optimization. The challenge is writing an optimized program using row order and cache blocking technique was complex. So the solution is we study online example and apply cache blocking to divide matrices into smaller blocks for better performance. The third one is debugging and runtime error. The challenge that we face is encounter logic error and incorrect output due to array boundary issues and loop mistake. So the solution is we use the dev C++ debugger to trace and contract error, especially in loop structure and index usage.
Thank you.